Now let's go over some additional examples that will help you on your week 9 homework. The second part of the homework, 15 through number 28. And also you may see a couple of these on your exam 2 this Friday. So the mean and the standard deviation of a sampled population are respectively, the first number they gave us is the mean of the population. So I'm going to call this and label this mu. And the standard deviation they're giving us 35.1. So these are the parameters. These are the mean and the standard deviation for the population. They want you to find the mean and standard deviation of the sampling distribution of the sample mean x bar for sample size of n equals 81. Round your answer to 1 decimal places. Remember, what they want right here is mean of the sampling distribution of sample mean. And you know, from going over those slides with me, mean of the sampling distribution of the sample mean is equal to the mean of the population, right? So therefore, without thinking, this first answer is simply 120.5. We were given the mean of the population, so it must be the same. Now the standard deviation, that one, standard deviation of the sampling distribution of sample mean, also called standard error. Let me write that down, standard error. That one, you have to use the formula, standard deviation of the population divided by square root of your sample size n. So let's plug that in. Standard deviation divided by square root of n is, well, remember the standard deviation they gave us is 35.1. And we're going to divide this by square root of n is 81. So that's 35.1 divided by square root of 81 is 9. Let me go ahead and type this in my calculator and get the answer, but let me first move this work over here. So these are the formulas that I was using. 35.1 divided by 9 equals, really, just 3.9. So we found the standard deviation for the sampling distribution of the sample mean using that formula, and that's it for number 1. Of course, later we'll use these to find the probability, but for that one, that was it. All right, the gestation time for humans has a mean of 266 days and a standard deviation of 24 days. For humans, right? This is for the population. So I'm going to label this. Let me use a different color pen. This 266 days is the mean of the population, and this 24 is the standard deviation for the population. If 144 women are randomly selected. Now they're randomly selecting 144, so that's my sample size. If n equals 144 are randomly selected, find the probability that they have a mean pregnancy between 268 days and 270 days. Now, these are the fun type problems. So, what you will need to do is, first of all, we need to know if it's okay for us to use the normal distribution. Well, is it or is it not? It is, right? Because look at the sample size. By the central limit theorem, as long as the sample size is at least 30, we can assume, I know even though they didn't say anything about the distribution of population, because our n is 144, our sample size is bigger, we can assume that the sampling distribution of sample mean is also normally distributed. So let's find the mean and the standard deviation and use the normal distribution to find this probability. All right, what's the mean? Mean of the sampling distribution is equal to the mean of the population, which is 266. Now, standard deviation of the sampling distribution is equal to standard deviation of the population divided by square root of the sample size. Now, what's that going to be? So we'll have standard deviation is given to us as what number? 24. And we're dividing that by square root of 144. That was our sample size. Now, that's a very nice number. 24 divided by what number? 12. So we got that the standard deviation for the sample mean, or called standard error, is simply 2. So highlight these two numbers. You need them. This is the mean. This is the standard deviation. Write down what we're trying to find. We're trying to find the probability that the pregnancy is in between 268 days, is longer than 268 days, but less than 270 days. That's what we're trying to find. And I'm going to use my technology. I'm going to use my StatCrunch to find this. But you will need these numbers. So, you know what? Let me try to write these numbers down on a little notepad so that when I go to my app, my StatCrunch, I know how I have these numbers. So I'm going to type up real quick. Mean equals 266. Standard error or standard deviation of this sampling distribution is 2. And what I need is probability that x is in between 268 and 270. I do wonder, guys. I just have my 21-week check. My baby's really big now, but I may want to use this to figure out when. Well, not this specific, because I'm not going to have a sample size at 144. It's just going to be 1 Sue. So not the sampling distribution, but maybe the regular normal distribution, assuming the population is normally distributed. But anyways, let's go to the StatCrunch. Oh, where's my calculator? Go to my math lab. I'm going to open up. This is my first time trying to use my StatCrunch on my iPad. I hope it works. Looks like it's going to work. Open StatCrunch. Everybody's talking about COVID. Open StatCrunch. Opened. Okay, that's good. Now let's go to Stat, Calculator, and click on Normal. How can we assume normal? Because the sample size was big. 144 was greater than 30. So we can use normal distribution. Now between, what were the two numbers? Well, first we gotta give them the mean. Remember, the mean was 266 days. The standard deviation is 2, because we found that out. I mean, that's the standard error that we had to calculate for the sample size of 144. And we're looking for the probability that x is in between 268 but less than 270 days. I wonder if you can see what I'm typing. Is this big enough? Can you guys see that? And then I will, and you know, if you're worried about, didn't you type or didn't you write it 268 is less than, I mean, like the symbol doesn't match, but remember, this is a continuous probability distribution, so it's okay. That's the same thing as saying x is strictly greater than or less than. All right, hit compute. That's my answer. That's my answer. Let me see if I can copy this. Oh no. Well, I don't know how to copy on my iPad, so I'm just going to type this in my notepad and then go back to my 1359. Okay. Going back to my note page, I got that the probability is approximately 0.1359. And how did I get that? You know, it'll be probably nice for me to take a screenshot of what I did. And then maybe I can attach that. I'll do that, guys. I'm going to take a screenshot of these. How do I take a screenshot on iPad? Like maybe this one? Oh, that works, guys. That worked. So I will attach the screen to that Word, that PDF, so that even if you're not watching this video, you still know how I got that probability. And I will come back and have see attached screenshot. But the other ones are going to be very similar. So let's try 2 more. But if you feel like you got something that looks just completely different, then you let me know, okay? All right, let's look at number 3. In one region, the September energy consumption levels for a single-family homes had a mean of, okay, I like it when they give me the mean of 1050 kilowatt per hour and a standard deviation of 218 kilowatt per hour. I think that's how I read these units. If 49 different homes are randomly selected, hello, 49 is our N value. And notice 49 is definitely greater than or equal to 30, right? So because of the central limit theorem, give me 1 second. I'm having the weirdest brain moment. I'm checking something. Yes, by the central limit theorem, the central limit theorem, we can assume a normal distribution for this sampling distribution of sample mean. So what's this? Find the probability that their mean energy consumption level for September is greater than, they want you to find the probability that X is greater than 1077. You know, on the previous video that took me about 15 minutes to record, I used the z-score and used the table. But with you taking this exam at home, just use StatCrunch because you have that technology available in front of your computer, but you need to know what you are typing into your calculator, right? So let's set that up. So first, I need to find the mean of the sampling distribution. Mean of the sampling distribution is equal to the mean of the population mean, which is 1050. So we know that. You just use that. But remember, you have to use a special formula to find the standard error, right? Or the standard deviation of sampling distribution of sample mean, which is going to be standard deviation of the population divided by the sample size square rooted. Now that's going to be 218 divided by square root of 49. 218 divided by 7. Hopefully it comes out to be a nice number. Let me type this in my calculator. 218 divided by 7 is... It's not the nicest number, but I'll use it. I'm going to go ahead and just round this. You know, it's so risky to round a problem in the middle of a problem. Round the answer in the middle of a problem, don't you think? Because you know how sensitive your My Math Lab is. They'll say, oh, it's incorrect just because your 10,000th number was incorrect. So maybe I will just leave it as 218 divided by 7. I don't know if my StatCrunch will let me type it, but this came out approximately, let me write it, approximately 31.14285,714. Now I'm ready to plug in everything I know into normal distribution calculator. That's the mean, that's the standard deviation, and what I want is the probability that X is greater than 1077. All right, I will need these numbers when I get to that page, so I'm typing these on my notepad real quick so that I can type these in. 218 divided by 7, which is approximately 31 point, give me 1 second, 14285, blah, blah. All right, and then I want X is greater than 1077. Let's go to StatCrunch to use the normal calculator. Okay, now I don't want in between. I want the standard where I get to just pick one inequality. The mean of this distribution is 1050. 1050. What's the standard deviation? Now, we got that to be 218 divided by 7, right? I just don't know if they're going to let me type in a fraction. I mean, like, why not? Accept it, hopefully. All right, now we want to find the probability that X is greater than or equal to, in this case, it's going to be the same. What number? 1077. And I hit compute. Oh, no. So you see, you know what they're saying? Invalid input for standard deviation. This value must be a number greater than 0. So it's not like an Excel calculator where I type in something like that and they actually evaluate it. So what I need to do is I actually have to divide 118 by 7. And then I will need to give them the decimal. And that decimal is 31.1428. 5714. And if you're wondering why do you have to be that accurate, it's because I want you to get the right answer when you are typing, when you guys are typing your answers in your my lab. And if you feel like you just got points taken off because of rounding, you write me an email, I'll go in. If your answer is very close, then I'll make sure to go and add points back. So the answer is going to be 0.19297. 0.19297. So if I round this to the nearest thousandth, that will be 0.193. 0.193. That will be my answer here, since they didn't really tell me how to round this. So this probability comes out to be 0.193. Alrighty, hope you're doing okay. I got one more, but after this one, I'm going to wait for your email, because I know you'll be studying. I know you'll be at least working on these assignments to get ready for your exam too. So if you ever get stuck, please let me know. All right, last one. In a lottery, you bet on a 6-digit number between 0000000 and 111111. Okay, for a $1 bet, you win $500,000 if you are correct. What's the chance though, right? Oh my. I can enter my birthday, like 031389, and say that, hey, that is my lucky number. Will I win $500,000? And you see the chance is very low. But let's see. For a $1 bet, you win a $500,000 if you are correct. The mean and the standard deviation of the probability distribution for the lottery winnings are, okay, they're gonna give us this. 0.5, that is 50 cents. And the standard deviation of 500. Okay, Sue figures that if she plays enough times every day, eventually she will strike it rich by the law of large numbers. Over the course of several years, look at her. She plays 1 million times. Oh, gosh. So how much money did she just spend? $1 million. Because she bet $1 every time. Oh gosh, okay. Let X bar denote her average winning. But maybe she wants something. Find the mean and standard deviation of the sampling distribution of X bar. Oh, okay. Now, we do know that the mean of the sampling distribution is equal to the mean of the population, which is given to us 0.5. As 0.5, right? That is 50 cents. So her winnings are going to be, or what should I say? Yes, her average winning is about 50 cents. On average, she's going to win 50 cents. But, they didn't really give us the N value in number. At least it didn't really look like a number because it was so big. But we're talking about the sampling distribution. How many times did she play? What's the sample size? She has 1 million, right? So guess what? Our N is 1 million. Oh dear. Why would she do that? N is 1 million. So if I want to find the standard deviation of the sample size, standard deviation of the sampling distribution of X bar, I'm going to have to divide the standard deviation of the population by square root of N. We know the numerator is 500 because we were given that number. But the denominator, I'm going to have to take square root of 1 million. Oh, dear. Okay, so what is that? What is square root of, 500 divided by square root of 1 million? That is going to be exactly half. That's going to be exactly half. Well, it's because, square root of 1 million will be 1,000, right? So the standard deviation comes out to be exactly half. So they wanted you to find the mean and the standard deviation of the sampling distribution of X bar. We found them. Her winnings are going to be around 50 cents. But that winning is going to vary with the standard deviation of 50 cents. So how likely is it that Sue's average winning exceed $1? Oh, they're wondering what's the probability that this winning is going to be greater than 1? Find the amount she paid and the amount she paid to play each time. Use the central limit theorem to find an appropriate answer. Why are we allowed to use the central limit theorem? Look at this crazy Sue. She played it million times, and million is definitely greater than 30. So guess where I'm going? I'm going to StatCrunch. Gonna go ahead and type in the mean is 50 cents, 0.5. Now, standard deviation also came out to be 50. And we're trying to see when our winnings are going to be, oh, I forgot, greater than 1. Winnings exceeding 1. So, greater than 1 and hit compute. Oh, no, invalid input for mean. This number, what? Oh, you see how silly I am right there? I type in 0,5. I meant to put 0.5 there. I'm sorry. All right, and then I hit compute. Oh, so the probability that my winnings are going to be greater than $1 is about 0.15. 0.1587. So I'll just round it to that much, and let me go back and write the answer. This is whoopsies, I was writing with an eraser, 0.1587. And I'll also take a screenshot of that and attach it to this PDF document and post this on Canvas too, in case you're not watching. So those are the 4 problems that I picked. But if you feel like they're more fun and challenging and just exciting problems that you and I can go over together, write me an email, okay? I hope you guys are having a wonderful week. And please let me know before Friday at 11 if you're not going to be able to take your exam from 11 to, what did I say? The time